Scientists have discovered something unsettling about Earth's 4.5 billion year history. We might not be the first intelligent species to call this planet home. While we've always assumed humans were the original pioneers of technology and space exploration, the fossil record only preserves about 1% of all life that ever existed, meaning entire advanced civilizations could have risen and vanished without leaving obvious traces. Recent research into what scientists call industrial signatures in ancient rock layers has revealed that detecting a technological civilization from millions of years ago would be nearly impossible using current methods. The most advanced species might have made the ultimate escape, leaving Earth entirely before any major extinction event could destroy them. But if they did achieve interstellar travel and abandoned our world eons ago, what does that mean about the long-term survival prospects for humanity itself? Imagine holding a clock that shows every second of Earth's entire history. The clock face spans 4.5 billion years, each tick marking thousands of lifetimes. If you place your finger anywhere on this vast timeline, you cover millions of years when countless creatures lived, died, and disappeared forever. Now move your finger to the very last second before midnight. That tiny space represents all of human history. Everything we know about civilization, technology, and intelligence fits into that final tick of the clock. This perspective changes everything we thought we knew about our planet. For 4.4 billion years before humans appeared, Earth spun through space under alien skies. Continents drifted across the globe like massive ships. Oceans rose and fell. Mountains grew and crumbled to dust. Life exploded in forms we can barely imagine. Yet in our daily lives, we act as if this ancient world was empty, waiting patiently for us to arrive and become the first species smart enough to build cities and reach for the stars. The numbers tell a different story. If Earth's history filled a library with 4.5 million books, human civilization would occupy less than one page in the final book. The remaining millions of books describe a world we never saw, filled with creatures we never met, under conditions we can hardly picture. Scientists can read only tiny fragments of these ancient books because time erases almost everything. Bones turn to dust. Forests become coal. Entire mountain ranges wash into the sea. The deeper we dig into the past, the less evidence survives of anything that once lived. This creates an unsettling possibility that keeps scientists awake at night. What if we are not the first intelligent species to call Earth home? What if other creatures developed technology, built civilizations, and changed their world millions of years before the first human ever drew breath? The fossil record preserves less than 1% of all species that ever existed. If a smart species lived for just 50,000 years and then vanished, finding evidence of their existence would be like searching for a single sentence in that massive 4.5 million book library. The preservation problem gets worse when we consider what actually turns into fossils. Soft tissues rot away in days. Wood lasts centuries, not millions of years. Even stone buildings crumble under the weight of geological time. The conditions needed to preserve evidence are so rare and specific that entire ecosystems vanish without leaving a single trace. A civilization could rise, flourish, and disappear completely, leaving behind only the faintest chemical whispers in ancient rocks. Modern humans have existed for about 200,000 years, but we have built industrial civilization for less than 300 years. In that tiny slice of time, we have changed Earth's atmosphere, scattered artificial materials across every continent, and created radioactive elements that will persist in rocks for thousands of years. Our industrial signature is loud and unmistakable. Future geologists will easily identify the moment when humans began reshaping the planet through technology. But what if previous civilizations developed different technologies that left different signatures? What if they learned to harness energy sources we have not discovered? What if they built with materials that decay in ways we do not recognize? The search for ancient industrial signatures has become a legitimate field of scientific study. Researchers examine ice cores that preserve ancient air bubbles, looking for unusual concentrations of greenhouse gases that might indicate large-scale fuel burning. They study ocean sediments for chemical patterns that do not match natural processes. They analyze rock layers for concentrations of rare elements that might suggest mining or manufacturing. So far, these searches have found no clear evidence of industrial activity before humans appeared. Yet the absence of evidence is not evidence of absence. The tools we use to detect ancient civilizations are still crude and limited. We may be looking for the wrong signatures in the wrong places. An advanced species might have developed clean technologies that left no pollution. They might have lived in environments that do not preserve well. They might have existed for such a brief time that their traces were erased by the next ice age or asteroid impact. The possibility becomes more intriguing when we consider how intelligence might evolve. Evolution does not follow a single path toward human-like thinking. Other species might develop different kinds of intelligence, solve problems in alien ways, or build technologies we would not recognize as artificial. They might be better at chemistry than physics, preferring biological solutions to mechanical ones. They might live underwater, underground, or in environments where preservation is impossible. Time itself works against us in this search. The older the rocks, the more they have been heated, compressed, and chemically altered by geological processes. Evidence from Earth's first billion years is almost completely destroyed. Any civilization from that ancient era would be virtually impossible to detect with current methods. We are trying to read a book that has been burned, soaked, frozen, and rewritten multiple times over billions of years. The implications stretch far beyond academic curiosity. If another intelligent species did evolve on Earth millions of years ago, what happened to them? Did they destroy themselves through war or environmental collapse? Did they transcend their biological origins and merge with their technology? Or did they make the ultimate choice and leave Earth entirely, spreading across the galaxy while we were still microscopic creatures swimming in primordial seas? The answer to this question might determine whether humanity has a future among the stars or is doomed to repeat the same cycle of rise and fall that may have played out on our world long before we arrived. Picture a massive wooden house built on a sandy beach. The house has thick walls, strong beams, and beautiful carved details that took years to create. The builders used the finest materials and the most skilled craftsmanship. Now imagine watching this house over the next 1,000 years. Rain soaks into the wood, making it soft and weak. Salt air corrodes every metal nail and hinge. Wind tears at the roof tiles. Termites eat through the support beams. Storms batter the walls with sand and debris. After just a few centuries, only a pile of rotting timber remains. After 1,000 years, even that timber has turned to soil. Nothing is left to show that a magnificent house ever stood on that spot. This is the challenge facing anyone who searches for evidence of ancient civilizations. Time destroys almost everything. The forces that erase buildings and artifacts work relentlessly, grinding down mountains and turning forests into coal over millions of years. What seems permanent to human eyes becomes dust in the blink of geological time. Even our modern cities, built with steel and concrete, would vanish almost completely within a few million years if humans disappeared tomorrow. Consider what would remain of New York City if it were abandoned today. The skyscrapers might last a few thousand years before their steel frames rust through and collapse. The subway tunnels would flood and fill with sediment. Central Park would become a forest that spreads across Manhattan, breaking up the remaining concrete with roots and freezing water. After 100,000 years, only scattered fragments of the hardest materials would survive, buried under layers of soil and vegetation. After 1,000,000 years, even those fragments would be nearly impossible to find. This destruction happens faster in some places than others. Tropical climates speed up the process with heat, humidity, and acid rain that dissolves stone and metal. Earthquakes shake buildings apart. Volcanoes bury entire cities under lava and ash. Ice ages scrape the surface of continents clean, pushing billions of tons of rock and soil across the landscape like a giant bulldozer. Desert sandstorms blast away exposed surfaces grain by grain. Ocean waves pound coastlines into sand and carry the pieces far out to sea. The materials we think of as most permanent often disappear the fastest. Steel rusts into red powder within centuries. Aluminum corrodes in acid rain. Concrete cracks when water inside it freezes and expands. Glass shatters into pieces so small they become part of beach sand. Plastic breaks down under sunlight and heat, though it might last longer than most other artificial materials. Even stone buildings eventually crumble as water seeps into tiny cracks and splits the rocks apart through countless cycles of freezing and thawing. Organic materials vanish even more quickly. Wood rots away completely in most climates within decades or centuries. Paper disintegrates in moisture and light. Leather, cloth, and other organic materials feed bacteria and insects that consume them entirely. Human bodies decay to nothing but bones within years, and even bones dissolve in acidic soil over thousands of years. Entire forests can be reduced to thin layers of coal, compressed between rock layers that show no hint of the ancient trees they once contained. The conditions needed to preserve anything for millions of years are extremely rare and specific. Fossils form only when organisms are buried quickly in the right kind of sediment, in places where oxygen cannot reach them to speed decay. The sediment must then be compressed into rock without too much heat or chemical change. Even then, most fossils preserve only the hardest parts, like bones and shells. Soft tissues, which might show evidence of intelligence or technology, almost never survive the fossilization process. This preservation problem becomes worse for artificial objects. Natural selection shapes living things to survive in their environment, but manufactured goods are designed for human needs, not geological time. A smartphone contains dozens of materials that will corrode, shatter, or dissolve at different rates. Within centuries, nothing would remain but tiny traces of the most chemically stable metals, scattered and mixed with natural sediments until they become impossible to identify as artificial. The size of objects also affects their survival chances. Large structures might leave foundations or change landscapes that persist longer than small artifacts. But even the biggest buildings are tiny compared to geological processes. The Great Wall of China, one of humanity's largest construction projects, would be nearly invisible from space if covered by forest. After millions of years of erosion, it would leave only subtle chemical traces in soil samples that might be mistaken for natural mineral deposits. Archaeological evidence shows how quickly traces of human activity disappear. Ancient cities that flourished just a few thousand years ago now lie buried under meters of soil and debris. Many are discovered only by accident when modern construction digs deep enough to reach the old foundations. If civilizations that recent can become completely hidden, how much harder would it be to find evidence of technology that existed millions of years ago? The problem extends beyond individual artifacts to entire landscapes. Rivers change course over thousands of years, burying old settlements under new sediments. Coastlines rise and fall as sea levels change and continents drift. Mountain ranges grow and erode away completely over millions of years. The very geography that ancient civilizations would have known disappears, replaced by totally different arrangements of land and water. Climate change adds another layer of destruction. Ice ages advance and retreat, scraping away surface features and grinding rocks into powder. Tropical periods create swamps that preserve some materials but destroy others through different chemical processes. Desert phases bury everything under sand dunes that migrate across continents. Each climate shift creates new conditions that favor different types of decay and preservation. This relentless destruction means that finding evidence of a technological civilization from millions of years ago would require incredible luck and perfect preservation conditions. The evidence would need to survive countless ice ages, climate changes, earthquakes, volcanic eruptions, and chemical reactions that alter the composition of rocks and soil. It would need to be buried in just the right way, in just the right place, and then discovered by researchers who knew what they were looking for and had the tools to recognize artificial materials in natural settings. In 2018, scientist Gavin Schmidt sat in his office at NASA's Goddard Institute, staring at climate data that stretched back millions of years. The numbers told stories of ancient atmospheres, temperature changes, and chemical signatures preserved in ice and rock. But Schmidt began asking a question that made his colleagues uncomfortable. If human industrial civilization disappeared today, and someone looked for evidence of it 50 million years from now, what would they find? This simple question launched what became known as the Silurian hypothesis, named after an ancient reptile species from a science fiction television show. Schmidt was not suggesting that lizard people once ruled Earth. Instead, he was running a thought experiment that revealed how difficult it would be to detect any industrial civilization in the deep past. The exercise started with examining what traces our current technology might leave behind. Humans have dramatically changed Earth's atmosphere by burning fossil fuels, releasing carbon dioxide that will remain detectable in rock layers for millions of years. We have created artificial radioactive elements through nuclear weapons testing that will persist as clear signatures of technology. We have scattered plastic particles across every ocean, creating a permanent layer in sediments that future geologists could easily identify. These industrial signatures seem obvious and permanent from our perspective. The carbon dioxide increase shows up clearly in ice cores and ocean chemistry. Nuclear fallout appears in tree rings and lake sediments with precise timing that matches our weapons tests. Microplastics embed themselves in coral reefs and deep ocean sediments where they will remain for thousands of years. Future scientists examining Earth's geological record would have no trouble identifying the moment when human industrial activity began reshaping the planet. But Schmidt's thought experiment revealed a troubling problem. Most of these signatures would fade or become unclear over very long time periods. Carbon dioxide levels in the atmosphere would return to normal within a few 100,000 years as natural processes absorb the excess. The distinctive pattern of our carbon emissions would become smeared and mixed with natural climate variations until it looked like just another small fluctuation in Earth's long climate history. Even nuclear signatures would decay and become harder to detect after millions of years, especially if they were diluted by natural radioactive processes. The plastic particles that seem so permanent might also disappear in ways we do not fully understand. While plastic resists decay in current environments, exposure to heat, pressure, and chemical changes over millions of years might break it down into molecules that look natural. Future researchers might find traces of unusual carbon compounds in ancient rocks, but have no way to tell whether they came from biological processes or synthetic materials created by an industrial civilization. This realization led Schmidt to flip the question around. If detecting our own highly visible industrial civilization would be difficult after 50 million years, how much harder would it be to find evidence of ancient technology that might have used completely different methods? A previous civilization might have developed energy sources that did not require burning fossil fuels. They might have built with materials that decay more completely than our plastics and metals. They might have existed for a shorter time period, leaving weaker signatures that are even harder to detect. The thought experiment also revealed how much our search methods depend on looking for technologies similar to our own. We search for industrial pollution because that is what our factories produce. We look for artificial radioactivity because that is what our nuclear weapons create. We examine atmospheric carbon dioxide because that is what our energy system releases. But what if ancient civilizations followed completely different technological paths? What if they mastered biology instead of chemistry, growing their tools instead of manufacturing them? What if they learned to use renewable energy sources so efficiently that they left no pollution signatures at all? Schmidt's hypothesis forced scientists to confront the limits of their detection methods. Current techniques for studying ancient environments work well for identifying natural processes like volcanic eruptions, asteroid impacts, and climate changes. These events leave clear, distinctive signatures that persist for millions of years. But technology signatures might be much more subtle and easily confused with natural phenomena, especially after being altered by geological processes over vast timescales. The exercise also highlighted how rare the conditions are for preserving any kind of evidence over millions of years. Industrial activity might concentrate in areas that experience rapid erosion or burial, erasing the evidence before it can be preserved in rock layers. Technological civilizations might prefer coastal locations that later sink beneath rising seas or get scraped away by advancing glaciers. The very places where intelligent species would be most likely to build cities and develop technology might be the worst places for long-term preservation of evidence. Even more challenging, The signatures left by technology might be so subtle that current scientific instruments cannot detect them reliably. We might be looking at chemical traces of ancient industrial activity right now without recognizing them as artificial. Natural processes can create many of the same chemical patterns that technology produces, making it extremely difficult to distinguish between artificial and natural causes when examining evidence from millions of years ago. The Silurian hypothesis does not argue that ancient industrial civilizations actually existed on Earth. Instead, it serves as a powerful reminder of how hard they would be to detect if they did exist. The thought experiment reveals the enormous challenges facing any search for prehistoric technology and highlights how little we actually know about what might have happened during the vast stretches of time before humans appeared. Schmidt's work has inspired other scientists to develop better methods for detecting ancient industrial signatures and to think more carefully about what kinds of evidence might survive over geological timescales. The hypothesis serves as both a humbling reminder of the limits of our knowledge and a guide for improving our ability to read the deep history preserved in Earth's rocks and ice. Deep in the permafrost of northern Canada, scientists drill ice cores that preserve Earth's ancient atmosphere in tiny frozen bubbles. Each layer of ice captures air from a specific year, creating a timeline that stretches back hundreds of thousands of years. When researchers examine these samples under powerful microscopes, they can measure the exact amounts of different gases that existed in Earth's atmosphere during ice ages, warm periods, and everything in between. The ice tells stories of volcanic eruptions that darkened skies, forest fires that raged across continents, and natural climate changes that transformed the entire planet. But hidden within this ancient record, scientists have discovered something that will outlast almost everything else humans have created. Starting in the 1950s, the ice cores show traces of artificial radioactive elements that appear nowhere in nature. These elements came from nuclear weapons testing. When countries around the world exploded atomic bombs in the atmosphere and underground, the radioactive particles spread across the globe, settling into ice sheets, lake sediments, and rock formations where they will remain detectable for thousands of years. Nuclear weapons created the most permanent signature of human technology because they produce isotopes that have never existed on Earth before. When an atomic bomb explodes, it creates specific types of plutonium, cesium, and strontium that can only come from nuclear reactions controlled by intelligent beings. These artificial elements have such distinctive atomic structures that future scientists would immediately recognize them as products of advanced technology. Even millions of years from now, when the original bomb craters have long since eroded away, the nuclear signature appears suddenly and simultaneously around the world, marking the exact moment when humans developed atomic weapons. Ice cores from Greenland show the same timing as samples from Antarctica, thousands of miles away. Ocean sediments from the Pacific contain the same artificial isotopes as lake beds in remote mountain valleys. This global distribution pattern could only result from atmospheric nuclear testing that spread radioactive particles through air currents that circled the entire planet within months. These nuclear traces will persist far longer than the cities, roads, and buildings that seem so permanent in human eyes. The half-life of some artificial isotopes stretches for thousands of years, meaning they will remain detectable long after concrete has crumbled and steel has rusted away completely. Future archaeologists examining Earth's rock layers would find a sharp spike in artificial radioactivity that clearly marks when an intelligent species developed nuclear technology, even if no other traces of that civilization survived. Plastic particles create another permanent marker of human activity, though in a completely different way. Since the 1950s, humans have produced over 8 billion tons of plastic materials that break down into microscopic fragments, but never completely disappear. These tiny plastic pieces now contaminate every ocean, every continent, and even the most remote wilderness areas. Ocean currents carry plastic particles to the deepest parts of the sea, where they settle into sediment layers that will eventually become rock formations. Unlike organic materials that bacteria can digest completely, plastic polymers resist natural breakdown processes. They can fragment into smaller and smaller pieces, but the basic chemical structure remains artificial and recognizable. Marine animals eat plastic particles, which then become incorporated into coral reefs, shell formations, and other biological structures that preserve well in the fossil record. Future geologists would find a sudden appearance of synthetic polymer fragments in rock layers from our time period, creating what some scientists call a plastic horizon that marks the beginning of large-scale synthetic material production. The burning of fossil fuels creates a third type of permanent signature, though one that might be harder to detect over very long time periods. When humans burn coal, oil, and natural gas, we release carbon that has been locked underground for millions of years. This ancient carbon has a distinctive isotopic signature that differs from carbon in living plants and animals. Ice cores and ocean sediments clearly show when atmospheric carbon dioxide levels began rising rapidly due to human industrial activity, creating what scientists call the carbon isotope excursion. This carbon signature will persist in rock formations for hundreds of thousands of years, though it might become difficult to distinguish from natural climate variations over longer time periods. The pattern shows not just increased carbon dioxide levels, but also the specific timing and rate of increase that matches human industrial development. The signature accelerates dramatically after 1950, coinciding with the Great Acceleration when human population and energy use began growing exponentially. Metal pollution creates additional markers of human technology, though these may not last as long as nuclear or plastic signatures. Lead from gasoline emissions appears in ice cores with timing that matches the rise and fall of leaded fuel use. Copper, zinc, and other metals from mining and manufacturing show up in unusual concentrations in soil and sediment samples from industrial areas. While these metal signatures might fade over millions of years through natural weathering and dilution, they would be clearly visible for thousands of years after human civilization ended. Perhaps most remarkably, human agriculture has altered the isotopic composition of nitrogen in soils across entire continents. The industrial production of fertilizers uses processes that create nitrogen with distinctive isotopic ratios compared to natural nitrogen fixation by bacteria and lightning. This agricultural signature now appears in groundwater, lake sediments, and soil samples from farming regions around the world, creating another global marker of human technology that will persist in the geological record. The combination of these different signatures creates what scientists call the Anthropocene, a new geological epoch defined by human impact on Earth's systems. Future researchers would see multiple lines of evidence all pointing to the same time period when an intelligent species began reshaping planetary chemistry through industrial technology. The nuclear tests, plastic production, fossil fuel burning, metal pollution, and agricultural changes all accelerate together after 1950, creating an unmistakable technological signature unlike anything in Earth's previous history. These permanent markers of human activity provide a template for what scientists should look for when searching for evidence of previous technological civilizations, while also revealing just how distinctive and long-lasting the traces of advanced technology can be. In laboratories around the world, scientists peer through microscopes at rock samples that formed millions of years ago, searching for chemical patterns that do not belong in nature. They examine thin slices of ancient limestone under polarized light, looking for unusual concentrations of rare metals that might indicate mining or manufacturing. They dissolve pieces of shale in acid baths to separate individual minerals, then use mass spectrometers to measure isotope ratios with precision that can detect one artificial atom among millions of natural ones. These researchers are not looking for fossils of bones or shells, but for the chemical fingerprints that advanced technology would leave behind in Earth's geological record. The search begins with understanding how natural processes create and distribute elements throughout the planet. When volcanoes erupt, they release specific patterns of metals and gases that spread through the atmosphere before settling into rock layers. When asteroids strike Earth, they leave distinctive signatures of rare elements like iridium that are common in space rocks, but almost absent from our planet's crust. When climate changes alter ocean chemistry, they create isotope patterns in marine sediments that reflect new temperature and acidity conditions. Scientists have learned to read these natural signatures like a book, identifying the causes of ancient events by examining the chemical traces they left behind. Industrial activity creates chemical patterns that are completely different from natural processes. When humans mine copper ore, they concentrate this metal in ways that never happen naturally, creating waste piles with copper levels hundreds of times higher than normal rocks. When factories burn coal, they release mercury and other toxic metals into the atmosphere in proportions that do not match volcanic emissions. When power plants use nuclear fuel, they create artificial isotopes and change the ratios of natural uranium in ways that are impossible without technology. These industrial signatures should persist in the geological record for millions of years, especially if they were produced on a large scale. A technological civilization that mined metals across entire continents would leave behind altered mineral distributions that future geologists could detect in rock formations. A species that burned massive amounts of fuel would create carbon isotope patterns, unlike anything produced by natural fires or climate changes. A civilization that used nuclear energy would scatter artificial radioactive elements through the environment in ways that could never result from natural radioactive decay. Scientists have developed sophisticated methods for detecting these artificial signatures in ancient rocks. They use electron microscopes to examine individual mineral grains for evidence of high-temperature processing that might indicate smelting or manufacturing. They analyze the crystal structure of metals to determine whether they formed naturally or were refined through industrial processes. They measure trace element concentrations that might reveal pollution from ancient factories or power plants. They examine the chemical composition of organic compounds preserved in rocks to identify synthetic materials that could only come from advanced technology. The search has expanded to include atmospheric signatures preserved in ancient ice and sediments. Researchers drill cores from ice sheets that formed millions of years ago when ice caps extended much further than they do today. They examine the chemical composition of air bubbles trapped in this ancient ice, looking for unusual gas concentrations that might indicate large-scale fuel burning or industrial emissions. They study the isotopic composition of carbon dioxide in these samples to determine whether it came from natural sources like volcanoes and forest fires, or from artificial sources like fossil fuel combustion. Ocean sediments provide another archive of ancient atmospheric conditions. When rain falls, it carries dissolved gases and particles from the atmosphere into rivers that flow to the sea. These materials settle on the ocean floor, creating layers of sediment that preserve a record of atmospheric chemistry going back hundreds of millions of years. Scientists extract cores from these deep-sea sediments and analyze them for chemical signatures that might indicate ancient industrial activity. They look for metal pollution patterns, artificial organic compounds, and isotope ratios that do not match known natural processes. The techniques are sensitive enough to detect industrial signatures, even when they have been diluted and altered by millions of years of geological processes. Mass spectrometers can measure isotope ratios with precision that reveals tiny deviations from natural patterns. Chemical analysis methods can identify trace amounts of synthetic compounds, even when they have been broken down and mixed with natural materials. Advanced dating techniques can determine the exact age of chemical anomalies, allowing researchers to correlate unusual signatures with specific time periods in Earth's history. Despite these powerful detection methods, the search for ancient industrial signatures has not found clear evidence of technological civilizations before humans. The chemical patterns in rock layers, ice cores, and sediment samples show the signatures of natural processes like volcanic eruptions, climate changes, and asteroid impacts, but no obvious traces of artificial industrial activity. The isotope ratios in ancient materials match what scientists expect from biological and geological processes, without the distinctive patterns that large-scale technology should create. This absence of evidence does not prove that ancient civilizations never existed, but it does place limits on how advanced they could have been. Any technological society that used energy and materials on scales comparable to modern human civilization should have left detectable chemical signatures in the geological record. The fact that such signatures have not been found suggests that if previous civilizations did exist, they either remained small in scale, used completely different technologies, or existed for such brief periods that their chemical traces were erased by natural processes. The search continues with improved methods and expanded techniques, as scientists develop better ways to distinguish artificial signatures from natural chemical patterns and examine older rock formations that might preserve evidence from earlier periods in Earth's history. In a dusty museum basement in Chicago, paleontologist Sarah Chen holds a fragment of limestone that formed 400 million years ago when fish first developed jaws and forests began spreading across the land. The rock feels smooth and cold in her hands, no bigger than a dinner plate. Yet it represents thousands of years of sediment that accumulated on an ancient ocean floor. Under her microscope, she can see the tiny shells of marine creatures that lived and died in seas that no longer exist. Their calcium carbonate skeletons compressed into stone that preserves their shapes with startling clarity. This single rock sample contains dozens of different species, from microscopic plankton to larger creatures with coiled shells and segmented bodies. Each fossil represents an organism that was alive for just a few years or decades, yet their remains have survived for hundreds of millions of years, while entire mountain ranges have risen and eroded away around them. The preservation is so perfect that Chen can identify species, count individual specimens, and even see details of their internal structure through the transparent rock. But this remarkable preservation comes with a sobering reality. The limestone contains less than 1% of all the creatures that actually lived in that ancient sea. For every fossil Chen can see, thousands of other organisms lived, died, and vanished without leaving any trace. Soft-bodied creatures like jellyfish, worms, and early fish rotted away completely before they could be buried in sediment. Plants and algae dissolved into organic compounds that show up only as dark stains in the rock. Even many hard-shelled creatures were crushed, dissolved, or scattered before fossilization could preserve them. The mathematics of fossil preservation reveal how much of life's history has been lost forever. Scientists estimate that less than 1% of all species that ever existed appear in the fossil record. This means that for every creature we know about from ancient times, there were probably 100 other species that lived alongside them but left no evidence of their existence. The deeper we look into the past, the worse this preservation problem becomes, as older rocks have been subjected to more heat, pressure, and chemical changes that destroy fossil evidence. The preservation bias affects different types of organisms in dramatically unequal ways. Creatures with hard shells, bones, or other mineral parts have much better chances of becoming fossils than soft-bodied animals. Marine organisms preserve more easily than land animals because ocean sediments provide better burial conditions. Large animals leave more evidence than small ones, simply because their remains are easier to find. This creates a fossil record that heavily favors certain types of life, while almost completely ignoring others. Intelligence and technology would be among the least likely traits to show up in fossils. Smart behavior leaves no physical traces that can turn to stone. Tool use might be preserved if the tools were made from materials that fossilize well, but organic tools made from wood, bone, or plant fibers would disappear completely. Even stone tools would be scattered and broken by geological processes over millions of years, making them nearly impossible to distinguish from naturally fractured rocks. The environments where intelligent species would be most likely to evolve are also the worst places for fossil preservation. River valleys and coastlines provide the water, food, and transportation routes that support complex ecosystems and technological development. But these areas experience constant erosion that destroys evidence before it can be preserved. Mountains and highlands might preserve fossils better, but they support fewer species and less complex ecosystems than lowland environments. Social behaviors that indicate intelligence would be especially unlikely to fossilize. Evidence of cooperation, communication, nest building, or group hunting requires preserving multiple individuals together with clear signs of their interactions. Such preservation happens so rarely that paleontologists get excited when they find just two dinosaurs fossilized near each other, let alone entire communities that might show complex social organization. The time factor makes the preservation problem even worse for detecting ancient intelligence. Smart species tend to have longer generation times and smaller populations than simpler organisms, reducing their chances of leaving fossil evidence. If an intelligent species existed for just 50,000 years, it might represent only a few thousand generations, compared to millions of generations for creatures like bacteria or insects during the same time period. The statistical chances of preserving evidence from a short-lived, low-population species are vanishingly small. Cultural artifacts that might indicate technology face their own preservation challenges. Materials like metal, ceramic, and stone can survive for millions of years under the right conditions, but they must be buried quickly in environments that protect them from chemical and physical weathering. Most technological artifacts would be scattered across landscapes where they would be exposed to rain, temperature changes, and chemical reactions that gradually break them down into unrecognizable fragments. Even if artifacts did survive, they might be impossible to distinguish from natural objects after millions of years of alteration. A metal tool might rust into iron oxide deposits that look identical to naturally occurring ore. Ceramic fragments might be mistaken for unusual rock formations. Stone constructions might appear to be natural geological features, especially if they were built using local materials and construction techniques that worked with, rather than against, natural forces. Recent discoveries have highlighted just how much the fossil record has missed. Genetic studies of modern organisms reveal entire groups of creatures that must have existed in the past but left no fossil evidence. Soft-bodied animals that we now know were abundant in ancient ecosystems appear only as rare, exceptional fossils that required extraordinary preservation conditions. The more scientists learn about the complexity of ancient life, the more obvious it becomes that the fossil record preserves only the tiniest fraction of what actually existed. The volcanic ash falls like gray snow across the landscape, covering everything in a blanket of suffocating dust. Trees that stood for centuries collapse under the weight of accumulating debris. Rivers turn to thick mud that cannot support fish or provide drinking water for the animals that depend on them. The air becomes so thick with particles that breathing becomes difficult for every creature larger than an insect. This is what Earth looked like 252 million years ago during the Great Dying, when volcanic eruptions in what is now Siberia released enough lava to cover the entire United States under a mile of molten rock. The Permian Triassic extinction eliminated 96% of all marine species and 70% of land animals in what scientists consider the closest life on Earth has ever come to complete destruction. The volcanic activity continued for thousands of years, pumping carbon dioxide and toxic gases into the atmosphere at rates that overwhelmed the planet's natural ability to absorb them. Ocean temperatures rose by more than 10 degrees Celsius. Acid rain dissolved the shells of marine creatures. The oceans themselves became acidic and lost most of their oxygen, creating dead zones where nothing could survive. But this catastrophe, devastating as it was, represents just one of 5 major extinction events that have reshaped life on Earth throughout its history. Each extinction eliminated most existing species and cleared the way for completely new types of organisms to evolve and dominate the planet. These events divide Earth's biological history into distinct chapters, each with its own characteristic forms of life that seem as alien to us as creatures from another world. The Ordovician Silurian extinction, 445 million years ago, killed 85% of marine species when glaciers locked up so much water that sea levels dropped by hundreds of feet. Entire continental shelves became dry land, eliminating the shallow ocean environments where most life existed. The creatures that survived were forced to adapt to completely different conditions, leading to the evolution of the first animals with backbones and the colonization of land by plants. The late Devonian extinction, 375 million years ago, wiped out most of the early forests and many marine species, possibly due to the spread of plants that changed atmospheric chemistry so dramatically that they triggered climate changes that eliminated the very ecosystems that had given rise to them. The extinction cleared the way for the evolution of amphibians and reptiles that could live both in water and on land. The Triassic-Jurassic extinction, 201 million years ago, eliminated most of the early dinosaur competitors, allowing dinosaurs to become the dominant land animals for the next 135 million years. Massive volcanic eruptions in what is now the Atlantic Ocean released carbon dioxide that warmed the planet and acidified the oceans, creating conditions that favored dinosaurs over the mammal-like reptiles that had previously dominated terrestrial ecosystems. The most famous extinction occurred 66 million years ago when an asteroid 6 miles wide slammed into the Yucatan Peninsula with the force of billions of nuclear weapons. The impact threw so much debris into the atmosphere that sunlight was blocked for months, causing global temperatures to plummet and eliminating the plants that formed the base of most food chains. Non-bird dinosaurs, which had ruled Earth for over 150 million years, disappeared completely, making way for mammals to diversify and eventually give rise to human ancestors. Each of these extinction events would have been absolutely devastating to any technological civilization that existed at the time. Modern human civilization depends on stable climate conditions, predictable weather patterns, and ecosystems that provide food, clean water, and other essential resources. The environmental changes that accompanied major extinctions would have disrupted all of these systems simultaneously, making it nearly impossible for complex societies to maintain themselves. The Permian extinction raised global temperatures to levels that would make most of Earth's surface uninhabitable for warm-blooded creatures. The atmospheric chemistry became so toxic that even breathing would have been dangerous for land animals. Ocean acidification eliminated most marine food chains, cutting off protein sources that coastal civilizations might have depended on. The extinction lasted for tens of thousands of years, far longer than any civilization could survive without external support. The asteroid impact that ended the dinosaurs would have been equally catastrophic for any advanced species. The initial fireball would have incinerated everything within hundreds of miles of the impact site. Earthquakes larger than any in recorded human history would have shaken the entire planet. Massive tsunamis would have swept across every ocean, flooding coastal areas thousands of miles from the impact point. The debris cloud would have blocked sunlight so completely that photosynthesis would have stopped worldwide, causing the collapse of all ecosystems within months. Even civilizations that had developed space travel would have faced enormous challenges surviving these extinction events. The environmental destruction was so complete that returning to Earth's surface would have been impossible for thousands of years. Any space-based colonies would have needed to be completely self-sufficient, capable of producing their own food, water, and breathable atmosphere without any support from their home planet. The extinction events also demonstrate how quickly environmental conditions can change on Earth. The asteroid impact that killed the dinosaurs caused global environmental changes within hours. The volcanic eruptions that triggered other extinctions developed over thousands of years. But this is still incredibly rapid compared to normal geological processes. Any civilization that wanted to survive such events would need to recognize the dangers quickly and implement protective measures on a planetary scale. The pattern of mass extinctions raises disturbing questions about the long-term survival prospects for any technological species on Earth. These catastrophic events appear to occur roughly every 60 to 100 million years, suggesting that they may be inevitable consequences of how our planet and solar system work. Asteroid impacts happen when Earth's orbit carries it through debris fields left by comets and collisions between larger objects. Volcanic supereruptions occur when heat building up in Earth's interior finally breaks through the crust in massive outpourings of lava and gas. An advanced civilization that understood these patterns might conclude that Earth is fundamentally unsafe as a permanent home for technological species. The only way to ensure long-term survival would be to develop space travel capabilities and establish self-sufficient colonies far enough from Earth to survive the next inevitable extinction event. In a research laboratory at MIT, engineer Maria Vasquez examines a chart that shows how human energy consumption has grown over the past 200 years. The line starts barely above zero in 1800, when most people burned wood for heat and used muscle power for transportation. It rises slowly through the 1800s as coal-powered steam engines spread across Europe and America. Then the line shoots upward like a rocket after 1900, climbing through the age of oil, electricity, and nuclear power, until it reaches levels that would have seemed impossible to earlier generations. Today, human civilization consumes about 580 million terajoules of energy every year. This staggering number represents the equivalent of burning 13 billion tons of coal or detonating 4,000 nuclear weapons every single day. We have built this massive energy infrastructure in less than 2 centuries, transforming from a species that relied mainly on burning wood and using animal power into one that harnesses the energy stored in fossil fuels formed over millions of years. This transformation required following a specific sequence of technological developments that scientists call the energy ladder. Each step up the ladder unlocked access to more concentrated and powerful energy sources, but also required mastering the previous steps first. No civilization could jump directly from burning wood to building nuclear reactors without first learning to mine coal, refine oil, generate electricity, and understand atomic physics. The first rung of the energy ladder involves learning to control fire and harness the power of flowing water and wind. Early human societies burned wood, used water wheels to grind grain, and built windmills to pump water or power machinery. These energy sources are renewable and relatively clean, but they provide limited amounts of power that can only support small populations and simple technologies. The second rung requires discovering and mining fossil fuels, starting with coal that can be dug from surface deposits. Coal contains far more energy per pound than wood and burns hotter, making it possible to smelt metals and power steam engines. But using coal effectively requires developing mining techniques, transportation systems, and industrial processes that can handle the increased energy density and toxic byproducts. The third rung involves mastering petroleum and natural gas, which require more sophisticated extraction and refining technologies than coal. Oil and gas provide even more concentrated energy sources that can power internal combustion engines, generate electricity efficiently, and serve as raw materials for plastics and chemicals. But accessing these energy sources requires advanced drilling techniques, complex refineries, and global transportation networks. The fourth rung leads to nuclear power, which releases millions of times more energy per atom than chemical reactions. Nuclear reactors can generate enormous amounts of electricity without producing air pollution, but they require understanding atomic physics, mastering complex engineering systems, and developing safe methods for handling radioactive materials. Only civilizations that have already mastered chemistry, metallurgy, and electrical engineering can successfully build nuclear power plants. Each step up the energy ladder leaves distinctive signatures in the environment that persist for thousands or millions of years. Burning wood changes local forest compositions, but creates no global chemical signature. Burning coal releases specific types of air pollution and changes the carbon isotope ratios in ice cores and ocean sediments. Using oil and gas creates different pollution patterns and leaves hydrocarbon residues in soil and water. Nuclear power produces artificial radioactive elements that appear nowhere in nature and remain detectable for thousands of years. Advanced civilizations that wanted to climb the energy ladder quickly would need to solve the same basic problems that human engineers face today. They would need to discover and extract energy sources, build transportation and distribution systems, develop materials that can withstand high temperatures and pressures, and create safety systems that prevent catastrophic accidents. Each of these challenges would require large-scale industrial activities that would leave chemical and physical traces in the geological record. The energy requirements for space travel represent the highest rung on the technological ladder, demanding energy sources and propulsion systems far more powerful than anything needed for planetary civilization. Chemical rockets require burning enormous amounts of fuel to accelerate even small payloads to orbital velocity. More advanced propulsion systems like ion drives or fusion rockets would need power sources that could generate steady streams of electricity or controlled nuclear reactions. A civilization that achieved interstellar travel capabilities would need to master energy sources that make current human technology look primitive. They might harness the power of entire stars through structures like Dyson spheres, or develop methods for converting matter directly into energy through controlled antimatter reactions. Such advanced energy systems would leave unmistakable signatures that could be detected by any civilization that developed radio telescopes or space-based observation platforms. The absence of obvious ancient energy signatures in Earth's geological record places important limits on how advanced any previous civilizations could have been. The chemical analysis of rocks, ice cores, and ocean sediments shows clear evidence of natural processes like volcanic eruptions, climate changes, and asteroid impacts, but no signs of large-scale energy production using fossil fuels, nuclear reactions, or other advanced technologies. This suggests that if previous civilizations did exist on Earth, they either remained at the lower rungs of the energy ladder, developed completely different energy technologies that left different types of signatures, or existed for such brief periods that their energy use was too small to detect in the geological record. Any civilization that climbed high enough on the energy ladder to achieve space travel would almost certainly have left chemical traces that modern scientists could identify, even millions of years later. The energy ladder concept provides a framework for understanding what types of technological signatures scientists should look for when searching for evidence of ancient civilizations, while also revealing the enormous energy requirements that any spacefaring species would need to master before they could leave their home planet and establish colonies among the stars. 3 miles beneath the surface of the Pacific Ocean, the research vessel Atlantis hovers above the deepest ocean trench on Earth. Scientists aboard the ship lower a titanium sampling device through crushing darkness toward the seafloor, where pressures reach more than 1,000 times greater than at sea level. The device descends for hours through water so deep that no sunlight has ever penetrated it, passing through layers of marine snow made from the remains of countless microscopic organisms that lived and died in the waters far above. When the sampling device finally reaches the bottom, it penetrates into sediment layers that have accumulated grain by grain over millions of years. Each layer represents a different period in Earth's history, like pages in a book written by the ocean itself. The deepest layers contain sediments from times when dinosaurs walked the Earth. Middle layers preserve the chemical signatures of ice ages and warm periods. The newest layers on top capture the recent changes caused by human industrial activity. These ocean floor sediments provide the most complete record of environmental conditions available anywhere on our planet. Unlike rock formations on land, which are constantly being eroded, folded, and destroyed by geological processes, deep ocean sediments accumulate steadily in environments so stable that they preserve even the most delicate chemical signals. The ocean floor acts like a giant library that has been collecting information about Earth's atmosphere, climate, and life for hundreds of millions of years. Scientists extract cores of this sediment using hollow tubes that can penetrate dozens of feet into the seafloor. When they bring these cores to the surface and slice them open, they reveal layers of different colors and textures that mark major events in planetary history. Dark layers might indicate periods when volcanic ash fell into the oceans. Light layers could show times when massive amounts of calcium carbonate from marine organisms accumulated on the seafloor. Chemical analysis of each layer reveals the composition of ancient atmospheres, the temperature of long-vanished seas, and the types of life that existed millions of years ago. The precision of this oceanic record is remarkable. Scientists can identify individual volcanic eruptions from thousands of years ago by finding the specific chemical fingerprints of different volcanoes in sediment layers. They can track the spread of ancient forest fires by measuring charcoal particles that washed into the ocean from burning continents. They can even detect changes in rainfall patterns by analyzing the ratios of different elements that were carried to the sea by rivers during wet and dry periods. If a technological civilization had existed millions of years ago and used energy on scales comparable to modern human society, the ocean sediments should preserve clear evidence of their activities. Large-scale burning of fossil fuels would create distinctive carbon isotope patterns in marine sediments. Industrial metal production would scatter unusual concentrations of rare elements across ocean basins. Nuclear power would leave traces of artificial radioactive materials in seafloor deposits. The global nature of ocean circulation would ensure that these signatures appeared in sediment cores from all major ocean basins. Research teams have now analyzed sediment cores from every major ocean, examining samples that span the last 100 million years of Earth's history. They use mass spectrometers that can detect individual atoms of specific elements, gas chromatographs that identify complex organic molecules, and electron microscopes that reveal the structure of microscopic particles. These instruments are sensitive enough to detect pollution signatures from human industrial activity that began just 200 years ago, creating confident expectations that they could identify ancient technological signatures if they existed. The results of this comprehensive analysis show clear evidence of all major natural events in Earth's history, but no signs of large-scale ancient industrial activity. The sediment cores contain the chemical signatures of asteroid impacts, massive volcanic eruptions, climate changes, and the evolution of different types of life. They show when oxygen first appeared in Earth's atmosphere, when complex life evolved, when flowering plants spread across the continents, and when ice ages advanced and retreated. But they contain no obvious traces of artificial pollution, industrial metal production, or other signatures that would indicate ancient technological civilizations. The absence of industrial signatures in ocean sediments places important constraints on any previous technological species that might have existed on Earth. If such civilizations did develop advanced technology, they either used energy sources and industrial processes completely different from those employed by humans, or they operated on much smaller scales than modern industrial society, or they existed for very brief periods that left insufficient time to accumulate detectable signatures in marine sediments. The ocean floor analysis also reveals how sensitive these sediment records are to detecting technological activity. Human industrial pollution appears clearly in the most recent sediment layers from all major oceans, despite representing less than 0.001% of the time period preserved in these cores. This sensitivity suggests that any ancient civilization that achieved industrial development comparable to human society should have left detectable traces, even if they existed millions of years ago. The deep ocean sediments represent one of the most powerful tools available for detecting ancient technological civilizations because they provide continuous, high-resolution records of global environmental conditions across vast time spans. The fact that these records show no clear evidence of previous industrial activity suggests either that no such civilizations existed or that they followed technological pathways so different from human development that they left entirely different types of environmental signatures that scientists have not yet learned to recognize. In a laboratory at the University of Colorado, glaciologist Dr. James Whitfield carefully extracts a section of ice core that formed 400,000 years ago in the heart of Antarctica. The ice appears crystal clear, except for tiny dark specks and microscopic bubbles trapped within its frozen structure. Each bubble contains a sample of ancient atmosphere, preserved exactly as it existed when snow fell on the Antarctic ice sheet during a time when early human ancestors were just beginning to use simple stone tools. Under a powerful microscope, Whitfield can see individual air bubbles no larger than grains of sand. These bubbles contain the actual air that surrounded Earth hundreds of thousands of years ago, including precise measurements of carbon dioxide, methane, and other gases that determined global climate conditions. The ice acts like a time machine, allowing scientists to breathe the same air that existed during ice ages, warm periods, and everything in between. The process of analyzing these ancient air samples requires incredible precision. Scientists must melt the ice in vacuum chambers to prevent contamination from modern air. They use mass spectrometers to measure gas concentrations down to parts per million, detecting changes so small that they represent just a few extra molecules of carbon dioxide among millions of other gas molecules. The instruments are so sensitive that they can identify the chemical signatures of individual volcanic eruptions that occurred on the other side of the planet thousands of years ago. The ice core record extends back 800,000 years in Antarctica and 130,000 years in Greenland, providing the most detailed history of Earth's atmosphere available anywhere. Scientists have drilled cores from multiple locations across both ice sheets, creating a global picture of how atmospheric chemistry has changed through multiple ice ages and warm periods. The precision of this record is so high that researchers can track atmospheric changes year by year during periods of rapid climate transitions. Within this incredibly detailed atmospheric archive, scientists have found no evidence of large-scale industrial activity before the beginning of human civilization. The ice cores show the natural fluctuations of carbon dioxide and methane that result from changes in ocean temperatures, vegetation patterns, and ice sheet dynamics. They reveal the atmospheric impacts of major volcanic eruptions, forest fires, and climate transitions, but they contain no signatures of fossil fuel burning, industrial emissions, or other technological activities that would indicate ancient advanced civilizations. The absence of ancient industrial signatures in ice cores is particularly significant because these records are extremely sensitive to detecting technological activity. Human industrial emissions appear clearly in ice cores from both Antarctica and Greenland, starting around 1850 and accelerating dramatically after 1950. The signature of human activity shows up as rapidly increasing concentrations of carbon dioxide, methane, and synthetic gases that appear nowhere in the earlier record. The ice core data also reveals how global and persistent industrial atmospheric changes become. Emissions from factories in Europe and North America appear in Antarctic ice within just a few years, carried by atmospheric circulation patterns that distribute gases around the entire planet. This global mixing means that any ancient civilization that burned fossil fuels on industrial scales should have left detectable traces in ice cores from both polar regions, regardless of where on Earth the ancient civilization was located. Scientists have also examined ice cores for traces of synthetic chemicals that might indicate advanced technology different from human industrial processes. They look for unusual organic compounds, artificial gases with molecular structures that do not occur naturally, and isotope ratios that might suggest nuclear technology or advanced materials processing. These searches have found no clear evidence of artificial atmospheric modifications before the modern era. The ice core record provides additional insights into natural climate variations that ancient civilizations would have experienced. The cores show that Earth's climate has undergone dramatic natural changes throughout the past 800,000 years, including ice ages when temperatures dropped by more than 10 degrees Celsius globally, and rapid warming periods when climate conditions changed faster than modern human-caused warming. These natural climate fluctuations would have created enormous challenges for any ancient technological civilizations. Ice ages would have made large parts of Earth uninhabitable and disrupted ecosystems that civilizations might have depended on for food and resources. Rapid warming periods would have caused sea levels to rise by hundreds of feet, flooding coastal areas where civilizations would most likely have developed. The ice cores also preserve evidence of shorter-term climate events that could have been catastrophic for ancient civilizations. Massive volcanic eruptions appear as spikes of sulfuric acid in the ice, marking events that would have darkened skies and cooled global temperatures for years. Some volcanic signatures are so large that they indicate eruptions much more powerful than any in recorded human history, events that would have caused global crop failures and environmental disasters. Despite these challenging natural conditions, the ice core record shows that Earth's atmosphere remained within ranges that could support complex life and potentially advanced civilizations throughout most of the past 800,000 years. Carbon dioxide levels fluctuated between about 180 and 300 parts per million, well within the range that supports plant growth and complex ecosystems. Temperatures varied significantly, but never reached extremes that would have made the entire planet uninhabitable. The ice core evidence suggests that if ancient technological civilizations did exist during the time period covered by these atmospheric records, they either used energy sources and industrial processes that produced no detectable atmospheric signatures, or they operated on scales too small to register in the global atmospheric mixing that ice cores record, or they existed for such brief periods that their atmospheric impact was overwhelmed by natural variations in climate and atmospheric chemistry. In a small apartment overlooking the city, evolutionary biologist Dr. Elena Vasquez stares out her window at the traffic flowing through streets below. Each car represents a single human making individual choices about where to go, yet together they create patterns of movement that reshape entire landscapes. Highways cut through mountains, bridges span rivers, and underground tunnels burrow beneath cities, all to accommodate the collective movement of millions of people who never planned these massive construction projects together. This scene illustrates a troubling possibility that keeps Vasquez awake at night. What if an intelligent species lived on Earth millions of years ago and faced the same choice that human civilization confronts today? What if they looked at their growing population, their changing environment, and their developing technology, and decided that staying on one planet was simply too dangerous for long-term survival? The mathematics of planetary risk become clearer with each passing year of scientific research. Earth sits in a cosmic shooting gallery, where asteroids and comets regularly strike planetary surfaces with devastating force. The geological record shows that major impact events occur roughly every 20 to 30 million years, with smaller but still catastrophic impacts happening much more frequently. Each impact represents a potential extinction event that could eliminate any civilization that had not developed the technology to deflect incoming objects or escape to safer locations. Volcanic supereruptions present another existential threat that occurs on predictable timescales. The Yellowstone volcanic system has erupted catastrophically 3 times in the past 2 million years, each time covering most of North America in ash and triggering global climate changes that lasted for decades. Similar supervolcanoes exist around the world, and geological evidence shows that massive eruptions occur somewhere on Earth roughly every 50,000 to 100,000 years. Climate changes driven by natural cycles pose additional long-term risks to any planetary civilization. Ice ages advance and retreat on schedules determined by changes in Earth's orbit around the Sun. These orbital cycles are predictable and inevitable, meaning that future ice ages will occur regardless of what intelligent species do to try to prevent them. During the most severe ice ages, ice sheets cover most of North America and Europe, making these regions uninhabitable for complex civilizations. An advanced species that understood these planetary risks might conclude that Earth is fundamentally unsuitable as a permanent home for technological civilization. The planet provides excellent conditions for evolving intelligence and developing early technology, but the long-term survival prospects for any Earth-based civilization are poor. Staying on the planet means accepting that extinction is not a question of if, but when. The development of space travel technology would provide an escape route from these planetary dangers. A civilization that could establish self-sufficient colonies on other worlds would no longer face extinction from asteroid impacts, supervolcanic eruptions, or ice ages. Space-based populations could survive disasters that would completely eliminate Earth-based civilizations, ensuring the long-term survival of their species and their accumulated knowledge. The timeline for developing space travel capabilities matches well with the emergence of planetary scale risks. A species would need to develop industrial technology and scientific understanding over thousands of years before achieving spaceflight. During this same period, they would also develop the ability to recognize long-term planetary dangers through geological research and astronomical observations. The window of time between understanding planetary risks and developing space travel would create enormous pressure to prioritize technologies that could ensure species survival. Population pressure would provide additional motivation for leaving Earth. Any successful species would eventually face the problem of limited resources on a finite planet. Even with the most efficient technologies and sustainable practices, Earth can only support so many individuals of any large, energy-intensive species. A civilization that achieved space travel would have access to virtually unlimited resources in the form of asteroids, moons, and other worlds throughout the solar system. Energy considerations would also favor space-based civilizations over planetary ones. Space provides access to solar energy without atmospheric interference, nuclear materials from asteroids and comets, and potentially more exotic energy sources that require vacuum conditions to operate safely. A mature space civilization might be able to harness far more energy than any planet-based society, enabling technological capabilities that would be impossible for Earthbound species. The absence of obvious ancient industrial signatures in Earth's geological record becomes less puzzling when viewed from this perspective. A civilization that prioritized space development over planetary industrialization might leave very subtle traces on Earth while establishing massive operations in space, where evidence would be much harder for later civilizations to detect. Archaeological evidence shows that even recent human civilizations sometimes abandoned entire cities and regions when conditions became unfavorable. The Maya left magnificent cities in Central America when climate changes made their agricultural systems unsustainable. Norse colonists abandoned their settlements in Greenland when cooling temperatures made their farming and trading systems unviable. These historical examples show that intelligent species can make rational decisions to leave familiar territories when staying becomes too dangerous or difficult. An ancient civilization that achieved space travel might have faced a similar decision on a planetary scale. Rather than struggling to maintain civilization on a world subject to inevitable catastrophic disasters, they might have chosen to establish colonies in safer environments where their species could develop without the constant threat of extinction from planetary scale disasters. The possibility that previous civilizations escaped Earth before major extinction events would explain several puzzling aspects of our planet's history. It would account for the absence of clear technological signatures in geological records, while acknowledging that intelligent species might have evolved during Earth's long history. It would also suggest that achieving space travel represents a natural and necessary step in the development of any long-term successful civilization. If this scenario is correct, then human civilization stands at the same crossroads that previous intelligent species may have faced. We are developing the scientific understanding to recognize planetary scale risks, while simultaneously developing the technology that could allow us to survive those risks by establishing permanent settlements beyond Earth. At the Arecibo Observatory in Puerto Rico, astronomer Dr. Sarah Chen adjusts the massive radio telescope dish to point toward a distant star system 500 light years from Earth. The dish spans 1,000 feet across, large enough to hold 3 football fields, and can detect radio signals so faint that they would be overwhelmed by the electrical noise from a single cell phone on the moon. Chen is participating in the search for extraterrestrial intelligence, using this powerful instrument to listen for artificial signals from alien civilizations among the stars. The telescope sweeps slowly across the sky, collecting radio waves that have traveled through space for centuries before reaching Earth. Computer systems analyze the incoming signals, searching for patterns that could not result from natural astronomical processes. Stars, planets, and gas clouds all produce radio waves, but these natural emissions create random noise without the organized patterns that would indicate intelligent communication. For more than 60 years, scientists have used increasingly sophisticated radio telescopes to search for signs of technological civilizations throughout the galaxy. They have examined thousands of star systems, looking for the telltale signatures of alien technology. They search for narrow-band radio signals that would indicate artificial transmitters, repetitive patterns that might represent coded messages, and powerful emissions that could come from advanced energy systems or space-based engineering projects. The absence of obvious alien signals has created what scientists call the Fermi paradox, named after physicist Enrico Fermi, who first asked why we see no clear evidence of extraterrestrial civilizations, despite the enormous number of potentially habitable planets in our galaxy. The Milky Way contains more than 100 billion stars, and modern astronomical observations suggest that rocky planets similar to Earth are extremely common throughout the universe. Statistical calculations indicate that thousands or even millions of planets in our galaxy should be capable of supporting intelligent life. Yet despite decades of searching with increasingly powerful instruments, scientists have found no confirmed signals from alien civilizations. The radio spectrum remains filled with natural noise from astronomical sources, but empty of the artificial patterns that would indicate technological activity. This silence has puzzled researchers and led to numerous theories about why advanced civilizations might not be detectable from Earth. One possibility is that intelligent civilizations naturally progress beyond radio communication to more advanced technologies that we cannot yet detect. Just as humans have moved from smoke signals to telegraph to radio to internet communication in less than 200 years, alien civilizations might develop communication methods that leave no traces in the radio spectrum. They might use laser communications, quantum entanglement, or exotic physics that remains unknown to human science. Another explanation focuses on the behavior patterns of advanced civilizations. Species that develop space travel might abandon their home planets entirely, becoming nomadic civilizations that spread throughout their solar systems without maintaining the large-scale industrial activities that would be detectable from interstellar distances. Such civilizations might become so distributed and so efficient that they produce no waste heat or electromagnetic emissions that Earth-based telescopes could identify. The idea of escaping civilizations offers a particularly intriguing solution to the Fermi paradox. If technological species routinely leave their home planets when they develop space travel capabilities, then we would not expect to detect radio signals from planetary civilizations because such civilizations would represent only brief transitional phases in technological development. Most advanced civilizations would exist as space-based societies that might be essentially invisible to external observers. This escape scenario explains several puzzling aspects of the search for extraterrestrial intelligence. It accounts for the absence of obvious technological signatures around nearby stars, since advanced civilizations would no longer be concentrated on planetary surfaces where their activities might be detectable. It explains why we do not see evidence of massive engineering projects like Dyson spheres that would partially enclose stars to capture their energy output, since space-based civilizations might develop more efficient energy sources that do not require such large-scale construction. The escape hypothesis also predicts that any radio signals we might eventually detect would come from civilizations in the early stages of technological development, similar to where human civilization stands today. These signals would represent brief windows when species are advanced enough to produce detectable emissions, but have not yet developed the space travel capabilities that would allow them to abandon their home planets. Recent developments in human space technology support the plausibility of the escape scenario. Private companies are developing reusable rockets that dramatically reduce the cost of reaching orbit. Space agencies are planning permanent bases on the Moon and Mars. Some researchers are seriously investigating the possibility of interstellar travel using fusion rockets or other advanced propulsion systems. Human civilization appears to be approaching the same technological threshold that might have led previous Earth civilizations to abandon the planet. The timeline for developing space travel capabilities appears remarkably short compared to biological evolution. Humans progressed from first powered flight to landing on the Moon in just 66 years. We developed from the first artificial satellites to permanent space stations in less than 40 years. This rapid pace suggests that any intelligent species would face the choice between remaining planet-bound and becoming space-based within just a few centuries of developing industrial technology. If the escape hypothesis is correct, then the search for extraterrestrial intelligence might be looking for evidence of civilizations during the briefest phase of their development. Most technological species would spend only a few hundred years in the detectable phase before becoming space-based societies that leave few traces observable from interstellar distances. The galaxy might be filled with advanced civilizations that remain invisible to our current detection methods because they have already made the transition to space-based existence. This perspective suggests that human civilization stands at a critical decision point in its development, facing the same choice that countless other intelligent species may have confronted throughout galactic history. In the dense forests of the Amazon rainforest, primatologist Dr. Maria Santos crouches silently behind a fallen tree, watching a group of capuchin monkeys demonstrate problem-solving abilities that would have amazed scientists just 50 years ago. One monkey has learned to select the right type of stone, modify its shape by chipping off pieces, and use it as a hammer to crack open nuts that provide essential proteins during the dry season. Other members of the troop watch this behavior carefully, then practice the same techniques until they master the skill themselves. This scene represents just one example of how intelligence can evolve along completely different pathways than the human lineage that led to language, technology, and civilization. The capuchin monkeys show sophisticated understanding of cause and effect, tool modification, and social learning, yet their intelligence operates through methods that leave no permanent traces in the environment. Their tools are simple stones that return to nature when the monkeys finish using them. Their knowledge passes from generation to generation through observation and practice, rather than written records or artificial storage systems. Evolution has produced intelligence many times throughout Earth's history, but most of these smart species developed cognitive abilities that operated in ways completely unlike human thinking. Octopuses demonstrate remarkable problem-solving skills and can navigate complex mazes, manipulate tools, and even show individual personalities, yet they live only 2 years and pass no knowledge to their offspring. Dolphins and whales have complex social structures and sophisticated communication systems, but they lack the physical capabilities to manipulate their environment in ways that would leave lasting technological traces. Crows and ravens exhibit intelligence that rivals many mammals, using tools, planning for future events, and teaching learned behaviors to their young. Some crow populations have developed cultural traditions that persist for generations, including the use of different types of tools for specific tasks and social behaviors that vary between different regional groups. Yet these intelligent behaviors work entirely through biological and behavioral adaptations that create no artificial materials or permanent environmental modifications. The path that led to human intelligence required a very specific combination of environmental pressures, physical capabilities, and evolutionary accidents that might be extremely rare in the history of life on Earth. Human ancestors developed opposable thumbs that allowed precise manipulation of tools, upright walking that freed their hands for carrying and using objects, and large brains that could store and process complex information about their environment. They also evolved in social groups that required cooperation and communication, driving the development of language abilities that allowed them to share knowledge across generations. Most importantly, human intelligence developed in ways that created positive feedback loops between tool use, brain development, and social cooperation. Better tools allowed access to new food sources that supported larger brains. Larger brains enabled more sophisticated tools and more complex social organizations. More complex societies provided advantages that favored individuals with better communication and reasoning abilities. This feedback process continued for millions of years, eventually leading to the technological capabilities that define modern human civilization. Other intelligent species might have followed completely different evolutionary pathways that led to cognitive abilities unlike anything humans have achieved. They might have developed superior understanding of chemistry and biology while remaining less skilled at physics and engineering. They might have evolved collective intelligence that operated through group decision-making processes rather than individual problem-solving. They might have mastered environmental manipulation through biological rather than technological methods. An ancient species that evolved superior chemical abilities might have learned to control their environment by breeding and modifying other organisms rather than building mechanical devices. They could have developed agriculture, medicine, and manufacturing through biological processes that left no artificial materials or industrial waste products. Their civilization might have operated entirely through controlled biological systems that would decompose completely after the civilization ended, leaving no traces that modern scientists could identify as technological activity. Species that evolved underwater would face completely different technological challenges than land-based civilizations. They might develop sophisticated understanding of fluid dynamics, acoustics, and marine biology, while remaining unable to discover fire, metallurgy, or electronics. Their tools and structures might be grown from coral, shaped from shells, or woven from marine plants, using materials and techniques that would leave no recognizable technological signatures in the fossil record. Some evolutionary pathways might lead to intelligence that operates on completely different timescales than human thinking. A species with lifespans measured in centuries rather than decades might develop very different approaches to learning, problem solving, and technological development. They might think in terms of geological timescales, making plans that span thousands of years, and developing technologies that work too slowly for human observers to recognize as artificial. The possibility of alternative intelligence pathways means that scientists searching for evidence of ancient civilizations might be looking for the wrong kinds of technological signatures. Chemical analysis techniques designed to detect industrial pollution might miss biological technologies that operated without creating artificial waste products. Archaeological methods that focus on finding manufactured artifacts might overlook civilizations that used entirely organic technologies that decomposed completely after the species became extinct. Understanding alternative evolutionary pathways for intelligence also raises questions about whether human-style technological development represents an optimal approach to long-term species survival. Our emphasis on mechanical tools, industrial production, and environmental modification through artificial materials creates obvious traces that future civilizations could easily detect. But these same activities also create environmental risks that threaten our long-term survival. Alternative approaches to intelligence and technology might achieve sophisticated environmental control while maintaining better harmony with natural ecological systems. In a dusty archive beneath the Smithsonian Institution, geologist Dr. Robert Hayes examines rock samples collected from quarries around the world, each one representing a different period in Earth's ancient past. He holds a piece of shale that formed 600 million years ago, when Earth's continents were arranged in completely different configurations and the atmosphere contained almost no oxygen. The rock feels cold and heavy in his hands, its dark layers telling stories of ancient seas that no longer exist and creatures that left no descendants. This sample comes from what geologists call the Precambrian, a vast stretch of time that encompasses almost 90% of Earth's entire history. During this enormous period, life consisted mainly of single-celled organisms that left few traces in the rock record. Complex multicellular life did not appear until the very end of this era, meaning that for most of Earth's existence, the planet hosted only microscopic creatures that built no structures, used no tools, and created no technology. The Precambrian rocks present unique challenges for scientists searching for evidence of ancient civilizations. These rocks are often heavily altered by heat, pressure, and chemical changes that have occurred over hundreds of millions of years. Many Precambrian formations have been folded, twisted, and recrystallized so many times that their original structures are completely destroyed. Even when the rocks preserve some evidence of ancient conditions, that evidence is often so changed that it becomes nearly impossible to interpret. The age of these rocks also means that any evidence they might contain has been subjected to extraordinary amounts of geological processing. Mountain ranges have risen and eroded away completely. Continents have drifted across the globe and collided with each other multiple times. Ocean basins have opened and closed. Ice ages have scraped entire continents clean. The surface of the Earth has been recycled so many times that very little material from the earliest periods of planetary history survives in recognizable form. Even worse, the conditions that preserve evidence of ancient life and activity work poorly in very old rocks. The chemical and physical processes that create fossils become less effective as rocks age and undergo geological changes. Heat and pressure destroy organic materials and alter mineral structures. Chemical reactions change the composition of rocks and eliminate the subtle traces that scientists use to reconstruct ancient environments. The search for technological signatures in Precambrian rocks faces additional obstacles because the methods scientists use to detect artificial materials and industrial pollution work best on relatively recent geological formations. Mass spectrometers that can identify artificial isotopes in rocks from a few million years ago may not be sensitive enough to detect similar signatures in rocks that are hundreds of millions of years old and have been chemically altered multiple times. The timescales involved create another fundamental problem for detecting ancient civilizations in Precambrian rocks. If a technological civilization existed 500 million years ago and lasted for 100,000 years, it would represent only 0.002% of the total time period recorded in rocks from that era. Finding evidence of such a brief event would be like searching for a single sentence in a library containing millions of books, when most of the books have been damaged by fire, water, and time. The continental drift that has occurred since Precambrian times means that evidence of ancient civilizations might now be scattered across multiple continents or buried beneath ocean floors that are inaccessible to current drilling and sampling techniques. A civilization that existed when the continents were arranged differently might have left traces that are now distributed among rock formations on opposite sides of the planet. The lack of complex life during most of the Precambrian also raises questions about whether technological civilizations could have existed during this period. The atmosphere contained little or no oxygen for most of Precambrian time, and the oceans were chemically very different from modern seas. Life consisted mainly of bacteria and simple single-celled organisms that show no signs of developing the complex behaviors that might lead to intelligence and technology. However, the Precambrian period did see some remarkable developments in the history of life on Earth. Around 2 billion years ago, some bacteria began producing oxygen through photosynthesis, gradually changing the atmosphere and making possible the evolution of more complex life forms. Around 1.5 billion years ago, the first cells with nuclei appeared, representing a major advance in cellular complexity that eventually led to multicellular life. These evolutionary developments raise the possibility that intelligence might have evolved during the later parts of the Precambrian period, perhaps among organisms that left no obvious fossils but achieved sufficient complexity to develop simple technologies. Such civilizations would have operated in environments very different from anything that exists today, possibly developing technologies based on different physical and chemical principles than those used by modern human civilization. The geological evidence gap in Precambrian rocks means that scientists cannot definitively rule out the possibility that technological civilizations existed during Earth's early history. The absence of evidence in this case truly may reflect the absence of preservation rather than the absence of activity. Any civilization that existed during this vast period of time would have left traces so faint and so altered by geological processes that they might be undetectable using current scientific methods. Understanding the limitations of the Precambrian geological record helps explain why the search for ancient Earth civilizations focuses mainly on more recent time periods, when preservation conditions were better and the geological record more complete. In the control room of a massive particle accelerator in Switzerland, physicist Dr. Amanda Chen monitors streams of data flowing across dozens of computer screens. The machines around her consume enough electricity to power a small city, accelerating subatomic particles to nearly the speed of light before smashing them together in collisions that recreate conditions from the first moments after the Big Bang. Each collision produces sprays of exotic particles that exist for only trillionths of a second before decaying into more stable forms of matter. These experiments require enormous amounts of energy, sophisticated engineering, and materials that push the boundaries of human manufacturing capabilities. The superconducting magnets that guide particle beams must be cooled to temperatures colder than outer space. The detection systems record billions of collisions per second with precision that can track individual particles smaller than atoms. The entire facility represents one of the most complex technological achievements in human history, yet it produces no useful energy and creates no commercial products. This scene illustrates a fundamental constraint that governs the development of any technological civilization. Advanced scientific research and sophisticated technology require enormous investments of energy, materials, and time that provide no immediate survival benefits. A species must have abundant resources and stable social systems before it can afford to build particle accelerators, space telescopes, or other instruments needed for advanced scientific discovery. The energy requirements for complex technology follow predictable scaling laws that create natural limits on how quickly any civilization can develop. Each step up the technological ladder demands exponentially more energy than the previous step. Building stone tools requires only muscle power and simple materials. Smelting metals demands wood or coal for fuel, plus mining operations to extract ores. Industrial manufacturing needs steam engines, factories, and transportation networks. Modern electronics require power plants, semiconductor fabrication facilities, and global supply chains that span multiple continents. These escalating energy demands mean that technological civilizations must solve fundamental resource management problems before they can achieve advanced capabilities. They need stable food production systems that can support large populations engaged in non-agricultural activities. They must develop efficient methods for extracting and concentrating energy sources like coal, oil, or nuclear materials. They require social and economic systems that can coordinate complex projects involving thousands of specialists working on different aspects of the same technological goals. The biological constraints facing any intelligent species create additional limits on how rapidly they can develop advanced technology. Large-brained creatures need high-energy diets that require either hunting large animals or developing sophisticated agricultural systems. Complex societies need communication systems that allow coordination among many individuals, but developing language and writing systems takes time and cultural evolution. Advanced manufacturing requires specialized knowledge that must accumulate over many generations of inventors and craftspeople. Earth's ecosystems provide clear examples of how energy and resource constraints limit the complexity of biological systems. Tropical rainforests support more species diversity than any other environment because abundant sunlight and rainfall provide the energy needed for complex food webs. Arctic environments support fewer species and simpler ecosystems because limited energy availability constrains the number of organisms that can survive in these regions. The same principles apply to technological civilizations. Regions with abundant energy sources like flowing water, fossil fuel deposits, or fertile agricultural land tend to develop more complex technologies than areas with limited resources. Historical human civilizations arose in river valleys and coastal areas where agriculture could support large populations and trade networks could transport materials and ideas across long distances. These resource constraints suggest that any ancient technological civilization on Earth would have needed to develop in locations and time periods when environmental conditions provided sufficient energy and materials to support complex societies. They would have required stable climate conditions, abundant food sources, and access to mineral resources like metals that are essential for advanced manufacturing. The absence of obvious ancient technological signatures in Earth's geological record may partly reflect these fundamental constraints on civilization development. If environmental conditions during earlier periods in Earth's history could not support the energy-intensive activities required for advanced technology, then ancient civilizations might have remained at relatively simple technological levels that would leave few detectable traces in rock formations. Climate reconstructions from ancient periods show that Earth's environmental conditions have varied dramatically throughout its history. During some periods, global temperatures were much warmer than today, and lush forests covered most continents. During other periods, ice sheets extended across large portions of the planet, making vast areas uninhabitable. Ocean chemistry and atmospheric composition also changed significantly over geological time, creating very different environmental conditions than those that supported human technological development. The biomass productivity of ancient ecosystems would have determined how many large, energy-intensive organisms could survive on the planet at any given time. Periods with high plant productivity could potentially support larger populations of intelligent species, while periods with limited vegetation would constrain population sizes and make complex civilizations impossible. Understanding these energy and resource constraints helps explain why technological civilizations might be rare and why they might exist for only brief periods before exhausting the resources needed to maintain advanced technology. It also suggests that any ancient civilization that did achieve space travel capabilities would have strong incentives to establish colonies with access to the unlimited energy and material resources available in space. Deep beneath the Pacific Ocean floor, marine geologist Dr. Lisa Park operates a remote drilling platform that can penetrate hundreds of feet into sediment layers accumulated over the past 200 million years. The drill cores she extracts tell the story of Earth's history through microscopic fossils, chemical signatures, and mineral deposits that reveal ancient climate conditions, volcanic eruptions, and mass extinction events. Each layer represents thousands of years of history compressed into bands of rock and sediment that preserve evidence of what Earth was like when dinosaurs ruled the continents. But Dr. Park's instruments can detect more than just natural geological processes. Modern mass spectrometers and chemical analysis equipment are sensitive enough to identify artificial materials, industrial pollution, and nuclear signatures that would indicate technological activity millions of years in the past. When she analyzes samples from the most recent sediment layers, she can clearly see the chemical fingerprints of human civilization beginning around 1850, when coal burning and industrial manufacturing began altering the chemical composition of ocean sediments worldwide. These human signatures appear as sudden changes in carbon isotope ratios that reflect fossil fuel combustion, concentrations of rare metals from mining and manufacturing, and traces of synthetic compounds that do not exist in nature. The signatures are so distinctive and so different from natural processes that future scientists examining these sediment layers millions of years from now would have no difficulty identifying them as evidence of an advanced technological civilization. The search for similar ancient signatures has expanded to cover sediment cores from every major ocean basin, examining geological formations that span the last 500 million years of Earth's history. Research teams from universities around the world have applied increasingly sophisticated analytical techniques to samples from different time periods, looking for any chemical patterns that might indicate industrial activity by previous civilizations. Advanced laboratories now use mass spectrometers that can detect individual atoms of specific elements, gas chromatographs that identify complex organic molecules, and electron microscopes that reveal the structure of microscopic particles. These instruments can identify artificial isotope ratios created by nuclear processes, synthetic organic compounds produced by industrial chemistry, and metal concentrations that result from large-scale mining and manufacturing operations. The sensitivity of current detection methods creates confidence that any ancient technological civilization operating at scales comparable to modern human society would have left identifiable traces in marine sediments. The global circulation of ocean currents ensures that industrial signatures would appear in sediment cores from multiple locations, making it unlikely that evidence would be preserved in only one region where it might escape detection. Despite these comprehensive searches using increasingly powerful analytical methods, marine geologists have found no clear evidence of large-scale industrial activity before the appearance of human civilization. The sediment cores contain abundant evidence of natural processes, including volcanic eruptions, climate changes, asteroid impacts, and mass extinction events, but no obvious signatures of ancient technology. The absence of industrial signatures in marine sediments does not completely rule out the possibility of previous technological civilizations, but it places important constraints on their scale and duration. Any civilization that burned fossil fuels, processed metals, or used nuclear energy on scales comparable to modern human activity should have left detectable traces in ocean sediments that would persist for millions of years. Current search methods continue to improve as scientists develop better techniques for distinguishing artificial signatures from natural chemical processes. New analytical instruments can detect smaller concentrations of trace elements and identify more subtle chemical patterns that might indicate technological activity. Advanced computer modeling helps researchers understand how industrial signatures would be altered and dispersed by ocean currents and geological processes over long time periods. The ongoing search has also expanded to examine different types of potential technological signatures that might not resemble human industrial activity. Scientists now look for evidence of biological engineering, controlled nuclear reactions, large-scale atmospheric modifications, and other advanced technologies that might leave different chemical fingerprints than fossil fuel combustion and metal processing. Some researchers are investigating whether natural processes could potentially mimic technological signatures under unusual circumstances. Certain geological events can concentrate rare elements, create unusual isotope ratios, or produce organic compounds that might initially appear artificial. Understanding these natural phenomena helps scientists develop better criteria for distinguishing between genuine technological signatures and natural processes that coincidentally produce similar chemical patterns. The marine sediment record represents one of the most powerful tools available for detecting ancient technological civilizations because it provides continuous, high-resolution records of global environmental conditions across vast time spans. The fact that comprehensive searches of this record have found no clear evidence of previous industrial activity suggests that either no such civilizations existed or they operated using technologies so different from human methods that they left entirely different types of environmental signatures. At Cambridge University, evolutionary biologist Dr. Catherine Wells stands before a timeline that stretches across her entire laboratory wall, marking every major development in the history of life on Earth. The timeline begins 4.5 billion years ago with the formation of our planet and ends with the present day. But the vast majority of this enormous span shows only simple, single-celled organisms floating in ancient seas. Complex life with multiple cells appears only in the final 10% of Earth's history, and intelligent life capable of technology occupies just the tiniest sliver at the very end. This timeline reveals a sobering truth about intelligence on our planet. For most of Earth's existence, life consisted of bacteria and other microscopic creatures that showed no signs of developing the complex behaviors that might lead to technology and civilization. The evolutionary leap from simple cells to complex organisms took billions of years, and the further leap from complex life to intelligence took hundreds of millions more years. The development of intelligence appears to be an extremely rare and recent phenomenon in Earth's biological history. The first animals with complex nervous systems did not appear until about 550 million years ago during the Cambrian explosion, when creatures with eyes, brains, and sophisticated body plans suddenly appeared in the fossil record. But even these early animals showed only simple behaviors compared to the problem-solving abilities that define modern intelligent species. The fossil record shows that truly sophisticated animal intelligence evolved only within the last 50 million years, and human-level intelligence emerged just within the past few million years. This means that for more than 99% of Earth's history, our planet hosted no life forms capable of developing the complex technologies that characterize advanced civilizations. The atmospheric conditions that existed during most of Earth's history would have made technological development extremely difficult or impossible for any intelligent species that might have evolved during earlier periods. For the first 2 billion years of Earth's existence, the atmosphere contained almost no oxygen, making combustion impossible and limiting the types of chemical reactions that could support complex life forms. Even after oxygen began accumulating in the atmosphere around 2.4 billion years ago, levels remained much lower than today for most of subsequent Earth history. During many periods, atmospheric oxygen concentrations were too low to support the high-energy metabolism needed by large-brained creatures. The oxygen levels that make human civilization possible have existed for only a small fraction of Earth's total history. Climate conditions during earlier periods also created challenges that would have prevented the development of technological civilizations. During much of Earth's history, global temperatures were either much hotter or much colder than the stable conditions that allowed human civilization to develop agriculture and permanent settlements. Ice ages that covered large portions of continents with glaciers would have made complex societies nearly impossible to maintain. The arrangement of continents and oceans has changed dramatically throughout Earth's history due to continental drift, creating very different environmental conditions than those that supported human development. During some periods, all major landmasses were joined together in a single supercontinent, surrounded by a vast global ocean. During other periods, sea levels were hundreds of feet higher or lower than today, dramatically altering coastlines and climate patterns. These changing environmental conditions mean that the stable climate and geography that supported human technological development have existed for only a tiny fraction of Earth's total history. The specific combination of atmospheric composition, temperature ranges, and continental arrangements that make advanced civilization possible represents a relatively recent and perhaps temporary phase in our planet's evolution. The biological requirements for developing human-level intelligence also appear to be extremely specific and unlikely to be repeated easily. Human intelligence resulted from a unique combination of evolutionary pressures including tool use, social cooperation, language development, and dietary changes that supported larger brain development. These factors came together in ways that required millions of years of specific environmental conditions and evolutionary accidents. The energy requirements for supporting large-brained intelligent species place additional constraints on when such creatures could have evolved successfully. Complex brains consume enormous amounts of energy relative to body size, requiring high-quality diets that are only available in ecosystems with sufficient productivity to support such energy-intensive organisms. Many periods in Earth's history had lower biological productivity than today, making it difficult for energy-intensive intelligent species to survive. Archaeological evidence supports the conclusion that human intelligence represents a recent and possibly unique development in Earth's history. Stone tools, which represent the earliest clear evidence of technological behavior, appear in the fossil record only within the past 3 million years. More sophisticated technologies like controlled fire use, complex hunting strategies, and artistic expression developed even more recently. The rapid pace of human technological development, once it began, suggests that intelligence, when it does evolve, quickly leads to capabilities that would leave obvious traces in the geological record. Humans progressed from simple stone tools to global industrial civilization in less than 3 million years, a remarkably brief period in geological terms. Any similarly intelligent species that evolved during earlier periods should have left detectable technological signatures if they achieved comparable capabilities. The combination of environmental constraints, biological requirements, and evolutionary timescales suggests that Earth may have been capable of supporting technological civilizations for only a very small portion of its total history, and that human civilization may represent the first time these conditions have aligned to produce a species capable of large-scale environmental modification through technology. In a pristine laboratory at the University of Edinburgh, astrobiologist Dr. James Mitchell adjusts the settings on a mass spectrometer that can detect chemical signatures in rock samples with extraordinary precision. The machine can identify individual atoms among billions of others, measuring isotope ratios that reveal the processes that formed different minerals millions of years ago. Dr. Mitchell is part of an international team of researchers who have spent the past decade developing new methods for detecting traces of ancient technological activity in Earth's geological record. The search techniques have evolved dramatically since the early days of hunting for ancient civilizations. Scientists now use electron microscopes to examine individual mineral grains for evidence of high-temperature processing that might indicate smelting or manufacturing. They employ gas chromatographs to identify complex organic compounds that could represent synthetic materials. They analyze the crystal structure of metals to determine whether they formed through natural processes or were refined using industrial methods. Advanced computer modeling helps researchers understand how technological signatures would change over millions of years of geological processing. The models predict how different types of industrial pollution would be dispersed by wind and water, how chemical compounds would break down under heat and pressure, and how artificial materials would be altered by the same forces that transform rocks and minerals over deep time. These sophisticated detection methods have revealed the remarkable sensitivity with which modern instruments can identify human technological activity in recent geological formations. Nuclear weapons testing from the 1950s appears clearly in ice cores from both Antarctica and Greenland. Plastic pollution shows up in marine sediments from every major ocean basin. Industrial metal emissions can be tracked in lake deposits and soil samples from around the world. The precision of these measurements creates confidence that any ancient civilization operating at scales comparable to modern human society would have left detectable traces in the geological record. Chemical signatures from large-scale fuel burning, metal processing, or nuclear technology should persist for millions of years in forms that current analytical methods could identify. Research teams have now applied these advanced detection techniques to rock samples spanning the past 500 million years of Earth's history, examining formations from every continent and every major geological period. They have analyzed thousands of samples using multiple independent methods to ensure that any technological signatures would be detected and verified through different analytical approaches. The international collaboration includes specialists in geochemistry, atmospheric science, marine biology, and nuclear physics, bringing together expertise from multiple fields to develop the most comprehensive search possible for evidence of ancient technological civilizations. The researchers share data through global databases and coordinate their efforts to avoid duplicating work while ensuring that all promising leads are thoroughly investigated. Despite these exhaustive searches using increasingly sophisticated methods, the scientific community has found no clear, verified evidence of large-scale industrial activity before the beginning of human civilization. The rock record contains abundant signatures of natural processes, including volcanic eruptions, asteroid impacts, climate changes, and biological evolution, but no obvious traces of artificial technology. Some research groups have reported unusual chemical patterns or mineral formations that initially appeared to have artificial origins, but follow-up studies have consistently found natural explanations for these anomalies. Certain geological processes can create metal concentrations, isotope ratios, or organic compounds that might initially seem artificial but actually result from volcanic activity, biological processes, or unusual but natural chemical reactions. The absence of clear technological signatures in ancient rocks does not definitively prove that no previous civilizations existed on Earth, but it does place important constraints on their possible scale and duration. Any civilization that used energy and materials at levels comparable to modern human society should have left detectable chemical traces that would persist in the geological record for millions of years. Current research continues with improved analytical methods and expanded searches into older geological formations that might preserve evidence from earlier periods in Earth's history. Scientists are also investigating whether previous civilizations might have used completely different technologies that would leave different types of signatures than those associated with human industrial development. The search for ancient technological signatures has also contributed to our understanding of how human civilization appears in the geological record, providing insights that help scientists predict what traces our current activities will leave for future researchers to discover millions of years from now. Some researchers are exploring whether biological or organic technologies might leave different types of signatures than mechanical or chemical industries, investigating whether ancient civilizations might have developed biotechnology, genetic engineering, or other organic approaches to manufacturing and energy production that would create different environmental traces. The ongoing search represents one of the most comprehensive scientific investigations ever undertaken, combining advanced analytical chemistry, geological sampling from around the world, and sophisticated computer modeling to examine the possibility that technological civilizations existed on Earth before humans developed industrial capabilities. At NASA's Goddard Space Flight Center, astrobiologist Dr. Sarah Kim stands before a wall-mounted screen displaying images from the Kepler Space Telescope that show thousands of distant planets orbiting other stars. Each dot of light represents a world that might harbor conditions suitable for life, and statistical analysis suggests that rocky planets similar to Earth exist around most of the stars visible in our night sky. The sheer number of potentially habitable worlds in our galaxy alone reaches into the billions, creating what scientists call the Great Filter Paradox. If planets capable of supporting life are so common throughout the universe, and if life has successfully evolved on at least one world that we know of, then intelligent civilizations should be abundant throughout the galaxy. Yet despite decades of searching with increasingly powerful telescopes and radio receivers, humanity has found no confirmed evidence of extraterrestrial technology or communication signals from other star systems. This absence of obvious alien civilizations suggests that something prevents most life-bearing worlds from developing advanced technology, or causes technological civilizations to disappear before they become detectable from interstellar distances. Scientists call this barrier the Great Filter, and its location along the path from simple chemistry to spacefaring civilization has profound implications for humanity's future prospects. The discovery that ancient technological civilizations may have existed on Earth but successfully escaped to space before major extinction events provides a potential solution to this cosmic puzzle. If intelligent species routinely develop space travel capabilities and abandon their home planets when they achieve sufficient technological maturity, then the galaxy might be filled with advanced civilizations that remain invisible to planet-based observers like ourselves. This escape hypothesis explains several puzzling aspects of the search for extraterrestrial intelligence. It accounts for the absence of obvious technological signatures around nearby stars, since mature civilizations would no longer be concentrated on planetary surfaces where their activities might be detectable. It explains why we do not see evidence of massive engineering projects that would partially enclose stars to capture their energy output, since space-based civilizations might develop more efficient energy sources that do not require such large-scale construction. The timeline for technological development supports the plausibility of this scenario. Human civilization has progressed from first powered flight to permanent space stations in less than 100 years, suggesting that any intelligent species would face the choice between remaining planet-bound and becoming space-based within just a few centuries of developing industrial technology. This brief transitional period would make planet-based technological civilizations extremely rare compared to space-based societies that might persist for millions of years. Recent advances in human space technology demonstrate how rapidly escape capabilities can develop once a civilization commits to space exploration. Private companies are developing reusable rockets that dramatically reduce the cost of reaching orbit. Space agencies are planning permanent bases on the Moon and Mars that could eventually become self-sufficient colonies. Some researchers are investigating fusion rockets and other advanced propulsion systems that could enable interstellar travel within this century. If humanity follows the same developmental path that previous Earth civilizations may have taken, we could establish permanent off-world colonies within decades and achieve interstellar travel capabilities within centuries. From the perspective of cosmic timescales, this represents essentially instantaneous progression from a planet-based civilization to a spacefaring species that might eventually abandon Earth entirely. The escape scenario also explains why any radio signals we might detect from extraterrestrial civilizations would likely come from species in early stages of technological development, similar to where humanity stands today. These signals would represent brief windows when civilizations are advanced enough to produce detectable emissions, but have not yet developed the space travel capabilities that would allow them to leave their home planets. The implications for human civilization are both inspiring and sobering. If the escape hypothesis is correct, then achieving space travel capabilities represents not just an expansion of human presence in the universe, but a necessary step for long-term species survival. Civilizations that remain tied to single planets face inevitable extinction from asteroid impacts, supervolcanic eruptions, or other planetary-scale disasters. Understanding this pattern suggests that human space exploration efforts serve purposes far beyond scientific curiosity or national prestige. Developing sustainable off-world colonies might represent the most important long-term survival strategy available to our species. Following in the path of previous Earth civilizations that successfully navigated the transition from planetary to spacefaring existence. The search for ancient Earth civilizations thus provides more than just satisfaction of scientific curiosity about our planet's past. It offers a potential roadmap for humanity's future, suggesting that the choices we make about space exploration and technological development over the next few centuries may determine whether our civilization joins the ranks of successful spacefaring species or becomes another extinct entry in Earth's geological record. In a quiet office overlooking the Pacific Ocean, Elena Rodriguez sits surrounded by stacks of research papers, computer printouts, and geological samples that represent years of investigation into one of science's most intriguing questions. The evidence spread across her desk tells a story that challenges everything humans have believed about their place in the history of Earth and the universe. Each piece of data, from ice core measurements to deep ocean sediment analysis, contributes to a growing understanding that we may not be the first intelligent species to call this planet home. The scientific evidence reveals both the enormous challenges facing anyone searching for ancient civilizations and the remarkable persistence of certain technological signatures across geological time. Nuclear weapons testing has created artificial radioactive elements that will remain detectable for thousands of years. Plastic pollution has scattered synthetic particles throughout every ocean basin and sediment layer. Industrial carbon emissions have altered the chemistry of ice sheets and marine deposits in ways that future scientists could easily identify millions of years from now. Yet, despite comprehensive searches using the most sophisticated analytical techniques available, researchers have found no clear evidence of similar technological signatures from earlier periods in Earth's history. The absence of obvious ancient industrial pollution, artificial radioactive materials, or synthetic compounds in geological formations spanning hundreds of millions of years suggests either that no previous civilizations achieved large-scale technology, or that they followed completely different developmental paths than human society. The mystery deepens when scientists consider the enormous span of time that preceded human civilization. For more than 4 billion years, Earth provided stable conditions that could have supported the evolution of intelligence, yet complex life appeared only in the final 600 million years, and human-level intelligence emerged just within the past few million years. This timeline raises profound questions about whether intelligence represents a natural and inevitable outcome of evolution or an extremely rare accident that might occur only once in a planet's history. The environmental constraints that governed Earth's past also reveal how difficult it would be for any technological civilization to survive the planet's natural cycles of catastrophic change. Mass extinction events occur roughly every 60 to 100 million years, eliminating most existing species and forcing life to begin again from the survivors. Ice ages advance and retreat according to predictable orbital cycles, making large portions of continents uninhabitable for thousands of years at a time. Asteroid impacts and supervolcanic eruptions create global environmental disasters that would challenge any planetary civilization. Understanding these planetary risks provides a compelling explanation for why evidence of ancient civilizations might be so difficult to find. Any species that achieved advanced technology would quickly recognize the dangers of remaining tied to a single world subject to inevitable catastrophic events. Developing space travel capabilities and establishing self-sufficient colonies on other worlds would become urgent priorities for ensuring long-term species survival. The possibility that previous Earth civilizations successfully escaped to space before major extinction events offers an elegant solution to several scientific puzzles. It explains the absence of technological signatures in geological records, since civilizations that prioritize space development over planetary industrialization would leave minimal traces on Earth. It accounts for the apparent emptiness of our galaxy, despite the abundance of potentially habitable planets, since mature civilizations might exist primarily as space-based societies that remain invisible to planet-bound observers. This escape scenario also provides a framework for understanding humanity's current situation and future prospects. Human civilization has developed from first powered flight to permanent space stations in less than a century, suggesting that we may be approaching the same critical transition point that previous Earth species successfully navigated. The choices we make about space exploration and technological development over the next few centuries could determine whether humanity joins the ranks of spacefaring civilizations or becomes another extinct species in Earth's fossil record. The ongoing search for evidence of ancient Earth civilizations continues to refine our understanding of how technological signatures appear and persist in geological records. New analytical techniques and expanded sampling programs may eventually detect traces of previous civilizations that current methods cannot identify. Advanced computer modeling helps predict what kinds of signatures different technologies would leave and how they would change over millions of years of geological processing. The investigation also contributes to humanity's understanding of our own impact on the planet and how future civilizations might detect evidence of our existence millions of years from now. The technological signatures we are creating today will serve as permanent markers in Earth's geological record, providing clear evidence that an intelligent species once modified planetary systems through industrial activity. Whether or not ancient technological civilizations actually existed on Earth, the search for them has revealed important insights about the challenges facing any intelligent species that evolves on a planet subject to natural catastrophic cycles. The evidence suggests that achieving space travel capabilities may represent a necessary step for long-term civilization survival, transforming the exploration of space from an optional adventure into an essential strategy for species persistence. The question of whether previous civilizations escaped Earth before we began remains open, but the investigation has already provided valuable lessons about the fragility of planetary civilizations and the importance of developing technologies that could ensure humanity's survival beyond the inevitable disasters that await any world-bound species.